Okay, so this is actually the palm probe experiments. This was done by, I think this was popularized by Ahmed Joel, who is no more, but his experiments were really fantastic. So we'll try to discuss like 3 or 4 experiments on this, and then we'll wind it up. And this is just a schematical diagram for any arbitrary molecule. Of course, here I have taken the liberty to show it is a triatomic molecule ICN. Right. So what it will do is the palm probe experiment, the way it is designed, it is like that. So initially the molecule will be in the ground state. Right. So this is a ground electronic state. Normally the way you look at the diatomic curve. So here you can think our diatomic means this is ICN. So I and center of mass of CN is here. Right. So in that sense, you can think of like CN molecule is falling apart from the iodine. So that in that sense, you can think about this is kind of a diatomic molecule, but it is not exactly because it's a triatomic molecule. So we'll have a potential energy surface. Anyway, so that is the idea. Is like molecule is initially in the ground state. Then this palm probe means there's a 2 laser pulse. Palm one laser is pumping from this ground electronics to state to the let's say here it is first excited state. And then when it is in the first excited state, this is it's a repulsive curve. So naturally the molecule is going to get dissociated. Right. So this is called half collision. Half collision in a sense is that is broken like that. Now when this CN fragment is falling apart from the iodine, which is in blue color, then I can have option of tracing this CN molecule. Right. Now, if it is completely fragmented, so that means it is completely separated from iodine. So CN will be somewhere here. Then I can have a laser pulse to probe the CN to take the CN to the excited state. Right. Now, when you take this CN molecule to the excited state, this CN molecule can be fluoresced back. Right. So this is kind of like laser induced fluorescence experiment you can think of. Right. So this the first one. This laser what you are taking, this one, this is actually pump. Right. This is the pump laser. Pump it is taking to the excited state, and when we are stressing the CN with some other delayed, of course there will be time delay. Now if I start this is at t equals to 0, then after certain time such that this is CN is going to be going to get separated, we can of course stress at every point, right? So that we can do it. We will discuss it in a couple of minutes. Now when CN comes here, we can set another laser, right, which takes to CN to the excited state. So this is CN in the excited state, CN star. Right. So that is basically probe. That means probing the product or any intermediates. So that's what it is called, the palm probe experiment. Okay. So that pump laser takes to the molecule from ground state to the excited state, and on the excited state it's a repulsive surface. So CN fragment is going to be separated from iodine, and then finally we set another laser which is called the probe laser, which is taking to the CN to the excited state, and then excited CN can fluoresce back. So that is called the laser induced fluorescence. Okay, so that is the way we can probe this and kind of stressing the product. Now we can detune this probe pulse, that means to the red in this direction. Then we can also find out the stress of the CN, or the you can say this is the kind of transition state region where it's not completely separated, and we should be able to find out the stressing of this transition state. So this is the way actually Professor Jewell he first he tried to do the real time femtosecond chemistry and try to trap the transition state, right? So this is kind of a schematic diagram what just to let you know how the palm probe experiments are going to be set up. Okay. Now, of course, like this experiment, it was supported by the theoretical calculation like wave packet dynamics. So they are complementary to each other. They explain the theory explains how this falling apart is also going to take place. Right? Okay, so so I'll discuss both of them simultaneously. So, so in the next slide, what I'm going to do is to give you a little bit of idea how the wave packet dynamics is formed. It's like a, I think if you remember, it's like a fourth postulate of the quantum mechanics. So that means time evolution of the wave packet, how it gives the region. So it is kind of like a classical mechanics what we have discussed the trajectory. Here it is going to be the wave packet, right? So as it is going to be a photo dissociation, so the ground state is involved and the excited state involved. So I am just considering two channel equation, Schrodinger equation, and of course it's a diabatic representation, means it's a one kind of representation where we describe the wave functions. This diabatic means very crudely, if I say, is that in this representation, in this basis, actually, you can think about the basis, because this is the ground state. Psi1 is the ground state wave function, electronic wave function. Psi2 is the excited state electronic wave function. Now we are doing the diabatic representation in a sense is that the kinetic energy operator is diagonal. I'll write in the expression in just the next line, and the potential energy is not diagonal, right? So that is kind of, look at here. This is simple time dependent Schrodinger equation. If you recall it, I equals del psi by del t, and h psi. H is the operator, Hamiltonian operator. Of course, here I am, as I am having two states, the psi is represented by the psi1 and psi2 in a column vector with respect to time, of course, time and coordinates both. Now, this Hamiltonian actually, as it is two states are involved, I am having Hamiltonian is the operator for total energy. So that is basically kinetic energy operator T. This is potential energy operator. Right, so this is this one is kinetic energy operator, and this one is going to be potential energy operator. Okay. Now kinetic energy is like this one. This is the matrix representation. This is identity matrix. That is because this is a two-dimensional problem. So I'm going from 1 0 0 1, and this is h square by twice mu d d square by dr square. So that is basically momentum operator, right? And two-dimension space. Plus you have the potential energy operator. Again, it is going to be two-dimension. Now this diagonal term are basically the two state potential. Like this V11 is potential for this one, right? And V22 is the potential for psi 2, the excited state, right? Then off diagonal terms is nothing but the coupling terms between these two states, right? So these here it is basically they will going to be same. So this is coupling terms between the state 1 and state 2. So that is V12 you can think of. This is normally we think about this is going to be the spin orbit coupling, right? So that's what is the coupling in the potential energy surface. Now this is in the diabetic representation. Diabetic, here is we have diabetic and adiabatic. So I just go for diabetic representation in a sense is that this kinetic energy operator, this one is diagonal, right? Whereas potential energy is not diagonal, you have off diagonal terms. So the coupling in this diabetic representation is due to the off diagonal terms in the potential energy operator, right? So that is the coupling term, and these are the energy terms for the potential energy surface. So that's what I have just and so V11, V22 are the ground state and excited state potential energy surface, right? And the off diagonal terms V12 or 21 are resulted from the interaction between two potentials. So those are basically the you can think about the spin orbit coupling, right? So okay, now this we have to solve this, right, with respect to time. Then only we know that at t equals to 0 we have the wave function, and then at certain times t, what should be the wave function. And this is a little bit tricky. I'll just give you conceptually how it is done. So this time evolution is it's basically done in this fashion. This is called the split operator method. The look at here the operator. Actually, the Hamiltonian is operating on this wave function. That's what we are going to do it basically how we get. So if we know the wave function at t, then this one, right, wave function, this is at t, then we can find out the wave function at t plus delta t. Delta t is means I am slicing the time with the time interval, and so therefore if I know the wave function at time t, what will be my wave function at t plus delta t, right? So that is the idea of the time evolution. Now it is done in a split operator method, right? So this is called split operator. I could have written this split operator method. Okay, so why it is split operator? Look at here. This is the kinetic energy and then potential energy. We should have just applied on this and then get this function. But there is a technical way to do it. We have to do it in a different way. So we splitted this potential energy operator, look at it, by 2. And half portion we are operating before kinetic energy operator, and half of this operating after kinetic energy operator. So that's why it is called the split operator method, the time evolution we do it. Now this is the technical way to do it. Actually, how do we do it? But for the timing, don't get into the detail, don't think about much, but just know that if you are going to go for further studies in this theoretical calculation, you will be able you should be at least getting introduced this. Now this split operator method, when it works like this, first we half the potential energy operator exponential operate on this. Now look at here, this wave function of course depends on the coordinates also. I did not write that. So this is a function of coordinates and time. Now this potential operator is a function of coordinates. That's what we discussed earlier, that if we have the potential energy in terms of the different geometries of the system, so that is nothing but the potential energy surface. So this is the actually the potential energy coming from the potential energy surface. Now that is cut it on the coordinate system. Now we can directly multiply this operator on this, right? No problem. Whatever the resultant we get after multiplication, that has to be operated by this kinetic energy operator. Now here you have to remember, this is potential energy operator in the coordinate space, right? So that means R1, R2, theta, or you can go for X, Y, Z, whatever. So this is in the coordinate space, right? Now look at the kinetic energy operator T. This is in the momentum space. Here it is, right? So then can we directly multiply this on this? Answer is no. So what we have to do, initially my wave packet is in the coordinate space. Then I multiply this potential energy operator, and that is also in coordinate space directly. But after that, when I need to operate this on this resultant function, what I have to do in between, I have to do the transformation of the wave packet, right? In between here, I have to do transform into momentum space, because this is in momentum. So if I don't go to the momentum space, I cannot multiply. So that is momentum space. This is a little bit new to this to you guys. So that is in the momentum space. Okay. So therefore, what I have to do it before multiplying this operator, I have to convert from coordinate space to the momentum space. So I have to convert into this. We need to go from coordinate space to momentum space, and then I can multiply this. So this is done by Fourier transform. I think you have learned this in the Fourier transform, learned in the NMR spectra. There was a portion there that what do you do when you go for the calculate the frequency domain, time domain to frequency domain, you do the Fourier transform, right?
Fourier transforms.
Yeah. So that is the way you have to do it, and the technical way to do it is an algorithm. It is called FFT, fast Fourier transform.
Fast Fourier.
Right. Komal, you might need this if you are joining this guy. Right. So I'm just giving you the information for that.
Yes, sir.
Yeah. So we have to. So what do we do? This wave function in the coordinate space, right? Then we multiply with this potential directly, because that is also in coordinate space. But then before operating the kinetic energy operator, which is in the momentum space, we need to do the first Fourier transform of that resultant wave function, go to the momentum space, and then multiply this operator. Right?
Yes, sir.
So the resultant function is now in the momentum space, right? But then I am having, again, I need to multiply half of the operator which is left, right? So what I have to do, again, I have to come back to the coordinate space from here, right? So at this stage, again, I have to convert into, do the FFT or inverse FFT, if you want to say that, go back to the coordinate space, right? And then multiply this. Ultimately, I will be getting this in the coordinate space. Okay, so that is the strategy. We do it in a numerical way. So finally, I am going to get this. Now, when I get this, so that is my now t. Again, I add delta t, and I keep on doing this for the time evolution for quite a long time. Right. And of course, this method is having error, which is delta t to the power cube. So the smaller is the time, my smaller is going to be the error slicing delta t, right? So that is the, so we have to adjust, because if you make it very small, then you need quite a long of time for computation time. So you cannot go arbitrarily small. So you have to be reasonably decide how much delta t you are going to get it, right? So with that, when you get the final wave function, now we can use this final wave function to define a lot of properties like correlation function, and which gives you the different property, absorption spectra and emission spectra and all these things. So we'll discuss this spectrum qualitatively, not quantitatively exactly how it comes. So now why really I'm going to go for this? This is because if you think about the wave packet dynamics, what I said here. So when this function moves, right, then there's this the ground state, I take this function here, wave function, ground state function, I excite this, goes to the excited state, and quantum mechanically the description is that how wave function evolves on this time on this potential energy surface, right? So that's what is the basically idea why we do need to go for this potential energy surface and evaluate do the time evolution, right? So now once we have this function, we will be able to get the property. So this is very briefly how do we do it, and the wave function propagation on the potential two-state potential energy surface, right? Now with this, I would like to discuss the actual spectrum, how we get it, right? Okay, let me clear my drawing. So this is like again just look at very carefully. I think you have already came across this. This is a photodissociation of again three body photodissociation, triatomic molecule like this. Now this one is the ground electronic state, right? And these are vibrational states like this. Under these vibrational states, you are going to have the rotational state. Those are not shown here, right? Okay, now what we do, this is a bound state, right? This state is bound state because these vibrational states are bound. Of course, above this, you are having a continuum level which are kind of dissociate. Those vibrational states can easily dissociate. Now these states are bound states, so that's why it is bound state. These vibrational levels are there. Now this is my ground vibrational state wave function molecule. Normally I would expect in the it will be in the ground state. Now this is the laser is taking to the excited state. Let's say first excited state. Right. So this is, if I take S0, this is my S1. You can think about in that way. So this is S0, and this is going to be kind of S1. You can have other states also, but for the timing, just stick to this. Now this is ground state, going to go to the, we are going to take it to the excited state here at t equals to 0. Okay. Now if we let this wave function evolve on time, the way like if you take this system here, because of this dissociative surface, the system automatically rolls on this and is going to go to the dissociation. Now the way wave packet does, we have to do the wave packet evolution based on this potential energy. The wave packet is going to move on time, so that is the time evolution. Now if the system is like this excited, then it can come back to this ground state, right? Depending on this time here, that picture can be generated using the wave packet dynamics like this. Wave packet as t equals to here. Now at t equals to t1, when it comes here, I take the overlap integral of this and this. So whatever the overlap integral, that gives me the intensity in this spectra left hand side, right? So there are 4 parts actually. If you look at here, the first part is this one. So that is bound state S0. Now it is laser is going to take it to the excited state. So that is it's a repulsive curve, that is 2. Now when it is on this surface, the system is going to roll over this, or the wave packet is going to move depending on what you are talking about. And then when the system comes back to this, then you are going to get spectrum, right? So this transition absorption you are going to get a broad spectrum. You know all these things like Boltzmann distribution, where you get the broad spectrum for the absorption. Now for the emission, when it comes back, because of the overlap integral with the ground state wave function, you are going to get the structure, right? So that is the fourth one you can look at it. Now we are going to get 2 different structure. Like one is broad one. This broad one indicates that this wave packets are coming back to this continuum. So you cannot really separate this out. So that is A part here. Now the B part, of course, you can look at the structure like that. Like when the wave packet comes back to this ground state, whatever the overlap integral you get, the time t equals to near about 0, you are going to get a spectrum. So this is going to be related to a v equals to 0. Right? Now wave packet is moving, wave function is moving on this. Now when it comes back to this v equals to 1, then if we do the overlap integral, we get this peak, right? But this intensity is going to be less because the overlap integral value is going to be less than the earlier one, right? So this is the way we get the structured emission spectrum, and of course the structure is related to the spacing of the vibrational levels, right? So that's what we are going to get it, right? Of course, here I would like to just mention little bit about how do we take the wave function at t equals to 0, that we have not mentioned it. So that is basically like this. So we have 2 states, t equals to 0, psi 1 and psi 2. So this is for the psi 1, this is psi 2. Now as we are taking this ground state by laser to this excited state, what should be the actual state representation initially, time t equals to 0? So that should be nothing but multiplied with the dipole moment vector, dipole moment operator. You can think about this. So that's why at t equals to 0, the initial wave function, this is the second part is going to be 0 because that was not populated. The first part we need to multiply with the row vibrational states. So this one, because that is the function I am taking, that is kind of a Gaussian, right? So that is phi diatomic potential if you take, and this is row vibrational state V and J. So V equals to 0, J equals to 0 if I am going for this one, right? And that we need to multiply with the dipole moment matrix mu1 for this state, because I am taking this. So this is mu into mu equals to E into R. So that mu is basically nothing but this kind of interacting with this state taking to this. So that is when light is shined on this. So that is the strategy. So this is row vibrational state of the ground state, multiplying with the dipole moment vector and taking it to the excited state. So that is kind of initially that should be my psi 1, and then psi 2 of course is going to be initially it should be 0 because it was not having contribution. So that is the vibration, the wave function we are going to take. This we can do because the dipole moment matrix is diagonal. So in a sense is that dipole moment matrix, if we are going to think about mu in general, that is going to be something like mu1 0, and then this is 0, and this is mu2. This is for the mu2 is for the excited state, right? So then we have psi 1. If I multiply with this like this, psi 1 here, and we are having psi 2, so ground state and excited state. So if I'm going to multiply like this to get this, right? So it's something like psi this one, If I multiply this, so I'm going to have psi 1 mu 1. Now psi 1 is nothing but the row vibrational state, this one, so that is this, and then this and this I need to multiply, so that is going to get this, and then when you multiply this with this, you are going to get 0. Right, so that's what it is, the function. Anyway, so don't get right now, don't get into this too much, but that is the way we generate. Okay, so that is t equals to 0, then it evolves over the time using the previous we discussed what we discussed, the time evolution operator, and then we take the overlap integral. So that is called the correlation, autocorrelation function, right? And that gives you the idea how it is going to work. Okay, so with this little bit of introduction, let me discuss the ICN photodissociation, how exactly it is going to look like. Okay, so this is the experimental result I have just quoted. You would not be able to understand what is this unless I put the potential energy surface. So, but before getting into that, let me just tell you. So as I said that when ICN is completely broken, like this is the picture, it's like this. I said this is the ground state ICN, wave function. This first excited state is 1, or here it is written V1, this is V0, V1, and this is the state V2 where CN is excited. Iodine is in the ground state, but CN is excited, right? Now these two colors, this is blue color is connected to this purple color is connected to this. Now what it is experimentally, what it is done, look at here. Now pump lambda 1, this is the pump laser, is taking to the excited state, first excited state, V equals to 1. Now the system is moving on this, right? When the CN is completely separated from this, or this quite far, so that is R infinity, this is infinity. Now it is lambda 2 means is the probe pulse, right? I'm giving the second pulse at this when R infinity, that means they are completely separated. And if I do this experiment, that means this is the pump laser at lambda 1, and the probe pulse I give here when R is infinitely separated. So that means CN is separated and taking to the excited state, and then CN is fluorescing back. So that is the laser induced fluorescence spectra what I am getting in the blue, right? So initially I get no intensity, right? That is because when CN is going to go from here to here, it takes time to reach to the CNs completely separated. Now here at the resonance condition with the CN, so once it is probe pulse is set here, when CN are coming, and you are going to get the intensity. So initially it is 0, then when it is reaches, then there is a plateau, because now CN are going to be resonant with this, right? But if I detune this probe pulse to the higher lambda or the lower frequency, that means R is now a star which is in the transition state region, so that is not separated. Now if you detune it, what happens? Initially also it will be 0, but then we are going to get a peak because this will be now taking to this. But if I wait for some more time, then this probe pulse is no more in the resonance condition with the CN, so the intensity is going to get reduced. Just see the contrast. When I probe at the separated, infinitely separated distance, so CN are coming, it is in the resonance, and then you are going to get the plateau like this. But if when you detune to the rate shifted lambda, then what we get? Initially, we are going to get peak because that will be in the resonance condition from here to here. But then when it moves this place, it's no more in the resonance condition. So this signal is going to get reduced, right? So that is the way we can explain. So that is this is actually theoretical calculation. It was done. This was the experiment was done by the Ahmed Joel's group. And this theory was done by somebody else, I think Mann's group in Germany. So what they combined together and they tried to explain this spectra. that initially wave function takes here, then you do the probe pulse delay at the lambda 2, what is basically r tends infinity. So that means when completely separated, it goes to the excited state Cn only, and Cn then it's fluoresces back, which is called the laser induced fluorescence. So this is actually laser induced fluorescence spectra. Here we are doing with respect to time, and of course this lambda is involved. Right? Now this peak is going to be plateau, because after certain time Cn is going to come, you are going to get the resonance condition. But if we detune this, this is going to be, peak is going to be like this. Initially it's going to peak, because this when it comes here it is going to be absorbing, but once it leaves this place, no more in the resonance condition. So this flattened part in this case is going to get reduced, right? So wave packet dynamics also reveals the same thing, right? So that is the kind of experiment and theory, they go hand to hand and explain how this real-time femtosecond chemistry is going to identify the course of falling apart of ICN on the repulsive excited state, right? So that means I can trap here also, I can trap here also. So we can find out what is the time scale it's going to fall apart. Okay, so for today I'm going to stop here this session, but we can have discussion if you have any question. Okay, so let me stop sharing here.